Hi there, this is Jacob Nash, and this is beginning a new course, Calc 2, but this is Calc 2 Quick, and this will be lesson 1 on definite integral review. So, let's give an overview of these lessons. So, just as a quick side note, typically I won't have any kind of introduction like this on a video, I'll just get right into it, but for this one, I wanted to say, if you're new to my channel, I've been making videos for about 5 years now. Started in 2020, and mostly I've made math videos, but I've also made other courses. Some of my psychology videos have been popular, and anyone that's seen my channel knows that I'm not a professional instructor, but I simply just try to explain things in the way that they make sense to me. But I'm starting a new approach with the Calculus 2 videos to better suit me and you. Now, how would this better suit me? Is that um, basically I have an inability to record as far as like drawing things. I used to be able to, but I currently do not possess any technology that can do that, and I felt like that there are already enough videos online explaining these concepts in great detail. So instead, I'll make these quick, almost like reviews. But that's why I say if you would like more in-depth videos, I highly recommend Professor Leonard. He is approximately 2.71 times better than me, probably more than that, really, whatever you want to say. uh better than me at making uh these videos, and because he's an actual professor, I'm just a nothing. And so yeah, he has videos that are like an hour and a half long, so I'm trying to, by contrast, make some that are shorter, that's supposed to serve the purpose of just kind of refreshing you. So that's just to let you know. Let's get started. This is really a review of a review. So Riemann sums. uh So remember that if we're trying to find area under a curve, that's what it means when we're finding an integral, right? But we have the indefinite integral, which we're going to talk about more in the next video, but we have the definite integral, and just like it sounds, definite means it's going to be the exact area under the curve. So we always get an answer, a number answer when we're finding definite integral, but when we're doing the indefinite integral, have a set of equations basically because of that plus c, but we don't have that for this. And just like for limits in calculus 1, how you had limits, but the limit longhand version of a derivative, and then you had a derivative. That's the same thing for this. We have these rectangles that we can visually use for Riemann sums, um, but we also have the shorthand of just doing the definite integral. But you still have to know this version too. So that's why we're reviewing it right now. So this picture right here, it's saying like, how could we find the area under the curve right here? We could use rectangles, and remember, the more that we get, if we get infinity rectangles, an infinite number, that is how we get the exact area. Because as you can see, with only four, it's pretty inaccurate because this is an overestimation because we see parts that are above that are extra. So imagine that this is like cake pan baking in the oven. We have this part that's above that's extra overestimation. We don't want that, right? So that's why we would have an infinite number of rectangles hypothetically, which is the same thing as what it means to do it and definite integral. And we're going to review about what it means to use the left or right of a rectangle. Also, there's midpoint, but that's pretty much obvious. This is in the middle of it for that. But this might seem confusing to some people, but the way that you look at it is the corner. So you see there's the left corner of all of these that are touching the curve or line or whatever. It's the left corner. So that's what we're talking about. We have right corners. It can get a little bit funky when we're going under the x-axis. Um, that's not as common, but you have to just make sure you think about the corner. But as you can see, there's sometimes when it underestimates and sometimes when it overestimates, depending on left and right. This is a perfect table that you can use that you'll just want to memorize so that you can remember how to know if it's an over or underestimation. It depends on two factors combined. So there's four possibilities. We could have left increasing, right increasing, left decreasing, right decreasing. If it's left and increasing, we have an underestimation. Like right here, this little part is still increasing. So it's like the cake, the cake pan is not at the top of it, or the cake baking is not at the top of it, it's slightly underestimation. But right here, it's a very slight overestimation. When it starts decreasing, then it gets, the steeper it is, the more of a, right here, big time overestimate for left decreasing, and then it's the opposite for right. Now we're going to talk about signed area versus actual area, which there's two names for both of those. I know that's so stupid. It's ridiculous when we have two names for things, but signed and net area are the same thing. Total and actual are the same. So for this right here, if we were talking about the signed area under the curve would likely be something close to zero, because for this interval, the whole thing, because we have almost the same amount under and above. So when you go under the x-axis, it subtracts. That's how I always remember it. If you go under the x-axis, it subtracts. That's why it's called signed area or net. But if it's total area, it's going to be A1 plus A2. So to say that again, A1 minus A2 is signed area. A1 plus A2 is the actual area. But keep in mind, whenever we take the definite integral, it automatically does the signed area. So if it subtracts, it just subtracts. If you're doing the Riemann sums, this also will give you the signed area unless you purposely do an absolute value so that everything will end up positive, which if you were asked to find the total area, that's what you would want to do. Let's look at an example. And for these examples, we are doing this. We have a little piece right here that goes under, but everything is positive for this example. So it looks like we're actually doing the total area, because this little piece here does not subtract based on how this is calculated. So if we're doing the left hand, this is what I'm talking about, how it gets funky. We're looking at this corner as being the left corner, so that's why this is what we use. Even though it's under, it looks a little bit weird. That's still the same. So we just basically add all these areas. Now, right here in this calculation, if you notice, well, what is the area of a rectangle? It is always length times height. Well, length times width, but in this case, we pretty much say height. But if you notice, the length is always the same, so we basically just add the heights and multiply it by the common length. Because the common length, it's always going to be the same length. That's the point. Like the rectangles are always going to be the same length, and in this case, it's 1, see? So that's why we put that off to the side, just so we don't have to write it multiple times beside the other things. So we distribute that out, and then we add the heights. How do you know the heights? It's always the y value. So you plug it into the equation, which the equation is ln of x. So we do ln of 0.5, ln of 1.5, etc. You add them, and we get 1.88. And how we know this is the left hand is because we use the left corners. The left corners are where it touches, although that's not really the best drawing because it kind of goes over it, but pretend like it does. If we did the right instead, look, this time the right corners are touching, so we're going to get a slightly different calculation. It's always shifted over 1, by the way. Here we start at the 0.5, but here we start at the 1.5, but we do go 1 further than we did before. There's no 4.5 on this one, which that's so horrible. That's supposed to be 3.5 right there. That's so bad handwriting. But it's 4.5 here. Same process. We were asked to do the midpoint. This madness here is because I got too lazy. This was previously recorded. Um, and basically, this time you would just do the middle, which is ln of 1, ln of 2, ln of 3, ln of 4. That's not that common that they would want you to do this, but sometimes you would. Keep in mind, though, if you add these two and divide them by 2, it doesn't give you the same thing as this. But this is the most accurate because the actual area ended up being 3.11. 3.18 is what we got for midpoint, so that's pretty close. Now let's review about the difference between these two things that are the same. Like how we can write and we need to know how to switch from one to the other. You will not have to calculate this actually, but you just have to write it and know how to switch between these. So this is the more friendly guy that we know. And basically this is our interval from A to B, remember? And this is the function that we're integrating, and then we're integrating in respect to x. So that's why there's dx. We could have f v dv, but that would be pretty stupid. But they might do something like that. You could see ft. That's definitely one that's common. But hopefully it's f of x, because I think it's stupid to have a different thing, unless it's a specific word problem that uses that letter. But here's the long version, which is this is what we use for the Riemann sums. This is a Greek letter that means sum. You might know that. That's what that means. So we have the limit as the number of rectangles goes to infinity. This is the area under the curve. That's what this thing is saying. As we have infinity rectangles, we get the area under the curve. And this is what it is. But like I said, you won't have to solve. So here's the function, but you see something funky in here. What the heck is that? Xi asterisk? In my Calc 1 videos, I didn't include the asterisks. You can or you don't have to. It doesn't really matter. But xi, definitely you'll see that. So xi is equivalent to this. A plus I times delta x. Delta x is the same thing as b minus a divided by n. So it's the change in x. And doesn't that make sense? We have these are always the x, the interval that in terms of x values. So b minus a, and then we divide by the n, how many rectangles we have. So that's multiplied by fxi. So whenever you see something like that, that means anytime you see an x, put xi. So we replace x with this. And that's going to make more sense when we look at an example. So here's an example. How do we go from a definite integral to a Riemann sum? So basically, I am going to draw a little bit on this one. So I know I say quick. These aren't going to really be quick. These videos are probably going to still be a little long, but not as long as like an hour and a half, which is what they probably would be if I completely explained it. So the things that you need to find are what is the f of x, and I need to know what a is, and I need to know what B is. This is going to be messy because I'm writing with a mouse, so I'm so sorry. I need to know what these things are. So f of x, well, here's the function, obviously. It's right here. And then A is 1, B is 3. So now I can create these other things. So we need a delta x that goes here. And how do we get that 2 over n? 3 minus 1 divided by n. N you just leave as n. So that's how we got that. So that's easy, right? Then we have to replace x with xi. And xi is equivalent to this. So we do 1 plus I times 2 over n. And that's exactly what we have here. And that's it. That's pretty easy, right? It's a little bit harder going the other way, which you'll also want to know how to do. Um, let me trash can these. So when we're going this way, instead we need to figure out like what is our xi, what is our delta x, and then we also want to know what our a is and b, so we can actually write the bounds. So how do we find what xi is? Well, it's usually going to be something that you see more than once, because remember we plug it in for x. I see 3 plus 3i over n more than once, so I know that's my xi, and I know that xi is equivalent to this, so the 3 must be my a, and then my delta x must be 3 minus n. And if b minus a equals 3 and a is 3, then 6 is what b must be, because 6 minus 3 would give us that 3 right there, or also right here. And then how do we know what the function is? We just get rid of this and just replace it with x, so it's the opposite. And there you go. So that's also not that hard, really, right? So that is it. That's the end of this review. I hope that this helped and stay tuned. Oh, by the way, here's some rules that you will want to remember. I'm not going to go through them right now, but maybe take a picture of this or something because these are all your rules that you're kind of just expected to memorize. This last one's kind of, you might want to review that if you don't remember. That's a kind of not super common thing. Really, the ones that are most used are these. So anyways, thank you for watching.